Hello everyone, my name is Ahmed Mowafy, a PhD candidate at University of Alberta. Today I'm going to talk about my paper titled Evaluation of the Seismic Response of an Innovative Hybrid Steel Timber Structure. I have divided my presentation into 6 main parts as shown here. Let's start with the introduction. As we all know, timber is a material that generally fails in a brittle manner. On the other hand, steel's ductile and predictable behavior makes it an efficient and reliable option to be combined with timber in what we call hybrid steel timber structures. To simplify, steel here works as an intelligent bodyguard who could save our valuable timber against different kinds of hazards. This actually could pave the way for increasing timber utilization in mid to high-rise buildings. Several novel hybrid steel timber structures have been developed over the past decade. I have divided them into 3 main categories based on the combination level, whether it's at the connection level, or at the component level, or at the building system level. So, our main objectives are to examine the seismic behavior of a new hybrid steel timber structure using numerical simulation and to develop a beam-to-column joint that could act efficiently between the steel and timber part. Now let's talk about our proposed hybrid steel timber structure. It consists of timber as a gravity load resisting system and steel as a lateral load resisting system. Our main challenge here is how to develop a timber joint that could secure an efficient load pass between the timber side and the steel part without having any local failure in the timber itself against lateral loads. Let's start to talk about the lateral load resisting system. We choose a moderately ductile concentrically braced frame where braces act as fuse elements so the buckling compression yield tension to dissipate the seismic induced energy, while the other parts of the structure should remain elastic. That's why we need to have a high rotational capacity for our joint that connect between whether it's the timber beam and the steel column or the timber beam and the other timber columns. So in conclusion, the joint that we are going to develop should act as a pure hinge, prevent any framing action in the timber side, accommodate with high drift ratios. Also, on the other hand, it should be practical, which means it should be easy to construct, small in size, and easy to protect from fire. All of those requirements are taken into consideration while designing and developing such a joint. So here is our developed joint. The main component of the joint are tapered U-shaped steel plate, a pin, a steel plate with folded end, and both of the plates are connected to the timber side using self-tapping screws. So here we could see the moment to rotation relationship of our joint, and we could see this joint could accommodate significant rotational demand until the bottom side of the beam touch the bottom side of this plate, so it will start to accommodate some stiffness as shown here. So we need to ensure that this connection will remain in the hinge zone during the significant earthquake event. So, using analytical investigation, we could calculate the rotational capacity of the joint as shown here. And we could also realize that the gap between the two sides, by adjusting it, we could easily control the rotational capacity of our joint. Now let's talk about the prototype building design. Three-story building located in Vancouver, which is a high seismic activity area, has been selected. We could see the gravity load resisting system consists of CLT slabs, glulam beams, and column, which all are timber and designed according to CSA 086. As mentioned earlier, our lateral load resisting system consists of a moderately ductile concentrically braced frame, and it is designed according to CSA S16. Following the normal procedure by satisfying the seismic loading, design the brace to be a sacrificial element using ductile design approach. Then the remaining parts of the steel frame should remain elastic using capacity design approach. Then finally, perform a structure analysis to check the drift ratios. Now let's talk about the development of our numerical model using OpenSeas. 3D fiber-based numerical model was developed to simulate half of the building, and with the rigid diaphragm assumption, we could only model the first frame as shown here, and the masses of those frames, of the adjacent frames, will be lumped to their adjacent column as shown. Here is our developed numerical model. So we used a force beam column element with steel 02 material. Also, we used fiber discretization for the HSS and the W sections that we have for the beams and columns. While on the timber side, we use only elastic beam column elements. Also, a leaning column was used to take into account the B delta effects of the other columns. High level of modeling for the steel gusset plates and timber joints was done by using rigid end zone and zero length element representing three springs here to take into account the inelastic properties of our gusset plate while the brace buckle, while a combination between tension gap element and stress material was taken into account to develop the timber joint materials that we want. Now it's time for response evaluation. Let's start with the pushover analysis. This is a pushover curve, shows a relation between the normalized base shear with respect to the design base shear from MPCC, while x-axis shows the ratio, the percentage between the roof displacement and the total height. So we push our structure to 3%. We could also see through this pushover curve that the braces start to buckle, then the tensile braces start to yield at this point, and also an overstrength of around 1.8 was observed for the braced frame. So the left curve here shows normalized steel brace forces with respect to their capacity, and we could realize the buckling and yielding response of the braces were probably captured in the model. While the right figure here shows that the inelastic lateral deformation of the frame tend to concentrate in the first story after the yielding of the braces. For the timber side, we could see that this graph shows the maximum rotation angle of the connection with respect to its rotational capacity along the story height. So we could see the maximum ratio of this is only 20%, which means that the timber joint here behaves as an idealized hinge, and it could successfully prevent any framing action to take place between the timber beams and column or the timber beam and the steel column. Now let's move to the nonlinear response history analysis. It was performed to evaluate the seismic induced demands in the proposed system when subjected to three types of scenarios: crystal records, Peninsula, and Cascadia. Here we could see three graphs that show the interstory drift profile along the building height for each scenario, and we could realize that the maximum or the largest inter-story drift demand equal to 2.5% occurs in the first story under Inisla ground motion IO9. On average, the inelastic lateral deformation of the braced frame is concentrated in story 1 as shown. Here also, those graphs show the steel column interaction along the story height per each scenario, so we could realize that it exhibits limited inelastic behavior at the first story. For the timber side, we could see that the left curve here show the timber joint maximum rotation angle with respect to its rotational capacity along the story height. So for 33 ground motions, we could only capture around 9% from the rotational capacity of our connection, which shows that it will remain within the hinge zone during the seismic event, and no framing action will be introduced between the timber beams and timber columns. Also, right figure here confirms that the timber column axial demand is only equal to the applied gravity loads. In conclusion, the proposed hybrid steel timber structure introduced into the study offers a viable option to resist both gravity loads and seismic-induced forces. A prototype building was selected, a new approach for the beam-to-column joint was introduced, and a methodology for modeling such a hybrid system was developed, and nonlinear static and dynamic analysis were conducted. From this study, we could see that the steel braced frame resists the lateral seismic loads, while the timber structure carries only the applied gravity loads. Also, the brace, buckling, and tensile yielding in the steel braced frame act as a ductility source under the seismic loads as required, and the proposed timber beam to column joint could successfully isolate our timber gravity load resisting system from the lateral load resisting system, and therefore no brittle failure was observed in this gravity load resisting system. Finally, I would like to thank my sponsors for their support, and thank you for listening to me today.